Hello, welcome back to our post session. In this session, we will have the presentations from the authors of the accepted papers of our workshop. I will share my screen and play the 5-minute videos of the papers, and then the authors will be here for 2-minute question and answering. So, okay.
Hello everyone. Next, I will show our paper, Domain Conditional Normalization for Test-Time Domain Generalization. Domain generalization means the model generalizes from multiple source domains to unseen target domains without access to any target data. The previous domain generalization methods can be mainly divided into 3 categories. The first is invariant representation learning. The second is data augmentation or feature augmentation. And the third is regularization techniques. However, these methods all lack the use of unlabeled test samples at inference. A few works are sought to address the above limitation. Some of them update BN parameters with target domain data using entropy minimization. Some of them adjust the weight of classifier with a few test samples to predict dynamically. Despite their great success, they still have the following limitations. Firstly, SGD update increases the inference time. Secondly, SGD update leads to catastrophic failure easily. Thirdly, batches of data are not necessarily available at inference. Lastly, we cannot guarantee that the domain labels are available at inference. The motivation for our paper is based on the following phenomena. First, the BN statistics are inconsistent for source and target domain. Second, the source statistics contain semantic and style information shared across domains. Third, the single target sample gives us a clue about the domain-specific information for a target domain. Our motivation is to infer the entire target BN statistics using source BN statistics and a single target sample. Based on the above phenomenon, we propose the method called domain conditional normalization. The framework of DCN is shown in the figure. The main idea of DCN is to simulate the statistics inference task in meta-learning framework. At each training iteration, it improves the instance statistics of a single imager and other source domain statistics into the autoencoders to infer the statistics for the domain of the single imager. We use different autoencoders to infer the standardization statistics and the rescaling statistics separately and use L2 distance loss to optimize the model so that the inferred statistics are close to the true statistics. Therefore, in the training phase, the meta-train task is the classification task, and the meta-test task is the statistics inference task. So the overall training loss is a combination of the CE loss and L2 distance loss. At inference time, the model infers the target statistics through each source domain and averages them to normalize the test data. The advantage of DCN is obvious. DCN only requires a forward propagation without SGD update at inference. What's more, DCN does not increase the inference time and memory overhead. Our method achieves state-of-the-art results on multiple datasets, such as PACS, VLCS, and Office Home. We do the ablation study to explore the impact of different components. The result shows that domain condition standardization brings a greater improvement. It is reasonable since that the standardization statistics between different domains have obviously greater difference than the rescaling statistics. We also do the evaluation study to explore the effect of where DCN is used. The results show that applying DCN in the first 3 blocks of the model works best. This is as expected, since the last block is the most relevant to semantic information. So the normalization statistics in the last block between different domains are similar. The above is the presentation of our paper. Thank you for listening.
Okay. I see the authors are here. Is there any questions for this paper from the audience? Okay. I have a question for the authors. So this work is using the one image from the target domain to estimate the statistics of the BN parameters. So what will happen if the target domain has a very high variance, and how to reliably infer the domain statistics even from one single example? So
Do you mean the high variance?
yeah, say you only use one target domain example to estimate the statistics in the BN parameters. But if the target domain is of high variance, can this method still be reliable?
I think the result is invariant for different examples, because we only infer the statistics using one target example, so the accuracy is not changeable. However, I think the inferred statistics is a little different for using different examples to infer. Yes, I think that is a phenomenon. Yes.
Yeah. Okay. Thanks for your answer.
Okay.
Let's go to the next paper.
Hello everyone, my name is Jinxin. Today I would like to present our work on the important problem of adversary domain adaptation. We view domain adaptation problem from the optimization perspective and point out a fundamental issue, in that the real-world data often present a balanced distribution where the large data clusters typically dominate and bias the domain process. To alleviate this issue, we propose a new concept of getting domain labels to achieve a dynamic adaptation, which allows each samples to be well studied and reduce long-tailed influence. Its core idea is to adaptively reduce the importance of this dominated training data that has been aligned, and timely encourage the domain discriminator to pay more attention to those easy-to-miss minority clusters, which ensures each sample can be well studied. Most adversary-based UDA algorithms tend to learn domain invariant representations by adversarially training the feature extractor and the domain discriminator in a min-max two-player game. As shown below, they typically use classification laws and the domain adversary laws for training. From figure shown at the bottom, we see that there is an obvious imbalanced situation with training going on, where some samples has been well aligned by the domain discriminator, but some samples are still understudied or not aligned well. To enhance the domain invariant representation learning, we introduced a dynamic adversary domain adaptation framework with the proposed goal labels. When correcting the domain adversary laws on a mini batch that contains both source and target domain samples, we replace the original domain labels of samples with changeable domain labels on the fly. Basically, we merge the alignment measurement and the domain label update in a single step. Formally, we leverage a non-parametric rounding operation to modify the original domain labels according to their predicted domain results by domain discriminator. A simple PyTorch-like pseudo code is shown below. The dynamic adversary domain adaptation framework with getting labels, a modification simply to the addition of line 9 and line 10 of the example code, which reveals its easy and effectiveness. We conduct some toy game of inter-transmos to indict the source positive samples to indict the effectiveness of the proposed method. The red aid, green subtract, and the black point markers indict the source positive samples, source negative samples, and target samples respectively. In figure at the bottom, we see that both baseline ignore the outlier samples, but in contrast, our method not only gets a satisfactory boundary between two classes in the source domain, but also covers those minority tail dates well and classifies them to the correct class. In that toy game, we also conduct experiments on the common used dataset, and our method also achieves the SOTA performance. In addition, we also conduct some emulation about some other gradient penalization and reweighting related method, and we can also see that our method achieves the best performance.
Okay, that's a presentation from the authors. Is the authors here in the Zoom? Okay. It seems that the authors haven't joined the room, so we will go to the next paper.
Our work focuses on the task of multimodal action recognition, and we investigate two questions. Firstly, we ask how helpful is each modality in a multimodal framework. For this, we quantify each modality's performance gain on the test dataset and obtain its contribution to the task, which can also be negative, as you can see on the right. However, to quantify the contribution, we need to evaluate on the test dataset, and hence, we need supervised labels. To detach ourselves from supervised labels, we propose a method to select the best modalities when no labels are present in a fully unsupervised way. As we don't have access to the labels, we do not know how each modality influences the performance. We extract 5 modalities, which are based on alpha poles, the Gunnar-Farnaback optical flow detection method, object detections from YOLO, and we combine them in our late fusion experiments. We investigate late fusion of multiple modalities for action recognition. In this example, the ground truth action is Cook, and we only use the 3 classifiers in the middle. This would result in a wrong prediction. However, if we use all of the classifiers, we would get a correct answer and also a higher performance. But if we also remove the modalities with a bad influence, the performance would become even higher. Modality selection is especially important in synthetic to real domain generalization, as certain modalities are more robust to domain shift than others. Moreover, real datasets often do not have any labels, so it is important to construct a systematic and supervised modality selection. Therefore, we train our models only on the synthetic sims for action dataset, and evaluate them on the real Toyota Smart Home and Edge Reactivity 3D. We train 5 unimodal classifiers on each extracted modality from Sims4Action and evaluate our late fusion models on the 2 real datasets. We propose how to minimize the domain gap and increase the performance by systematically selecting modalities which increase the late fusion performance. We first define a metric which quantifies how each modality influences the late fusion performance on the test dataset. For this, we compare the average difference of the combination with the modality M to the accuracy without it. This metric is positive if including the modality leads to a performance gain on average, and negative if adding the modality leads to a performance decline. The calculated contribution of each modality on all datasets is listed in the table below. It's interesting to see that the RGB modality generalizes the worst on real data, perhaps due to the large appearance changes, whereas the YOLO modality, which is the simplest one, generalizes the best. Next up, we have our unsupervised modality selection framework. We use 2 metrics for the selection. Firstly, we use the maximum mean discrepancy between the embeddings of the unimodal action classifiers. And secondly, we use the correlation between the predictions of these classifiers. We then compute modality selection thresholds and choose only modalities on which both metrics have a consensus. The details behind the threshold computation are inside the paper. We first focus on the correlation between the predictions. The correlations are illustrated in the chord plots and show how each 2 pairs of modalities are correlated. The lower correlations are visualized with thinner arches. We believe that a high correlation between correct predictions is statistically more likely than a correlation between wrong predictions, since there is only one correct class and multiple incorrect possibilities. We aggregate the correlation for each modality and compute the threshold for each test dataset. The red values belong to modalities which are below the threshold and will be discarded by this metric. We then focus on the discrepancy metric. We compute the maximum mean discrepancy for all modality pairs and plot it into these matrices where high values correspond to brighter colors. A high discrepancy is associated with a low agreement between classifiers, and hence to a lower performance. Therefore, we choose only modalities with a low discrepancy value, which is below the threshold. Again, these modalities which are above the threshold are colored in red and discarded by this metric. The final results show that the predictions correlation and the maximum mean discrepancy have reached the same conclusion as our contribution metric, which dealt with supervised labels. And we have reached these goals although we did not use any ground truth labels for the correlation nor the discrepancy.
Okay. Is the author here for this
I'm
paper?
here.
Yeah. Hi. So is there any questions from the audience for the author? Okay. Is there any questions? Okay. I have one question for your paper. So you tested your framework on the task of action recognition, but I'm wondering, can you apply this to other tasks other than action recognition?
Yes, that's a very good question. We listed that in the limitations of our approach because it's still not tested to other tasks. But in a follow-up work, I'm now working on medical segmentation from different modalities there. When you extract the features and compute the discrepancy between them, you can see how they generalize to other imaging modalities in medical segmentation. So this approach is extendable also to other tasks. And it gives a really nice intuition behind what means to select good sources of information, because typically you want the features to be really well aligned, because you would not learn a very good model when the features are disentangled too much in the latent space.
Yeah, that's a very good work. Thank you. Thank you for your answer.
Thank you.
Thanks. Let's go to the next paper.
Hi, I'm Kim Boon Ko, and I'm here today to present our paper, Consistency Regularization for Domain Adaptation. Some background and problem and task our paper is trying to solve before we go through our method. Semantic segmentation is a popular task in computer vision where we obtain pixel-wise class predictions from an input image. However, image task requires a lot of label data, and this is especially so for semantic segmentation, which requires pixel-wise annotations. To overcome this problem, one solution is to obtain labels from syntactic data, but there's usually a mismatch between the two domains. Unsupervised domain adaptation, UDA, is an attempt to solve this problem by developing models that can overcome this distribution mismatch. In our paper, we present a new regularization method for self-training that makes use of correlation between pixel-wise class predictions to improve UDA performance. Now, to provide a brief overview of our method. Firstly, to reiterate our problem statement, we have images that are from two different domains, a source domain and a target domain, where only the source data is labeled. Using these two different datasets, we're going to train a network that has high performance on the unlabeled target domain. As the two domains are usually mismatched, a network that is naively trained only on the labeled source data typically have poor performance on the target data. Overall training of our method is composed of three distinct components. The first is supervised training using labeled source images. Second is self-training using unlabeled target images. And third is consistency regularization. For the first component, supervised training on the source domain, we use the standard cross-entropy loss for semantic segmentation. The second component of the training process is self-training, where we use a teacher network to produce pseudo-labels from unlabeled target data. These pseudo-labels allow us to train our student network on the unlabeled target domain, besides the source domain in our previous step. For the third component of our training, we incorporated an additional regularization technique called consistency regularization into the self-training process. It is a technique used to encourage networks to make consistent predictions that are invariant to perturbations. As most applications of this method are in image classification tasks, we propose to further enhance it for semantic segmentation. Different from image classification problems, semantic segmentation tasks have a property where their pixel-wise class predictions are correlated with each other. By comparing each pixel with each other, we can model this correlation into a similarity matrix to further enforce consistency between outputs from teacher and student networks. In our paper, we use different methods such as cosine similarity, KL divergence, and cross entropy to model this correlation into a similarity matrix. We then use this similarity matrix in our third training component, consistency regularization loss, by performing a mean square error between similarity matrices of the student and teacher network. Our theory is that by enforcing consistency in not only the class-wise predictions in the second component, but also in its structure, we can further minimize the divergence between the source representation and the target representation. After going through our method, I will do a quick presentation on the experiments we conducted, as well as the results obtained. We use cityscapes as our target domain, and GTA 5 and Cynthia as our source domains. For network architecture, our implementation is heavily based on DA Former, which proposes an updated UDA architecture based on transformers. In this slide, we present our experimental results. By incorporating our consistency regularization method, we were able to improve from DA Former's performance on both GTA 5 to Cityscapes and Cynthia to Cityscapes problems. Most notably, we were able to obtain substantial improvements on the road and sidewalk categories, especially on the Cynthia to Cityscapes problem. We further verify this improvement in our qualitative analysis and attribute this improvement to our method's effectiveness in generating more accurate pseudo-labels. On the left, we present some pseudo-labels generated during the training process, and we can observe that more accurate pseudo-labels were generated for the road and sidewalk categories. With this, we've come to the end of our presentation. Thank you.
Okay, is the author here? Yeah, I see the author. Okay,
Hi,
is there...
yeah, I'm here.
Yeah, okay. Is there any questions from the audience? Okay, so I have a question actually about this paper. Like, in the paper, you mainly combine your method with the DA former method. Do you ever try to combine your consistency regulation with other methods for segmentation?
That's a very question. Actually, that is something I'm gonna try next time. That means implementing the regularization into other self-training frameworks. Yeah, but in this case, DA former actually had a very completed open source framework on the GitHub, and we found it easiest to incorporate this method into the framework.
Okay, thanks for the answer. Okay, now let's go to the next paper.
Hello, my name is Wei. I'm from the Institute of Computer Graphics and Vision at the Graz University of Technology. In this video, I present you the work of a PsycDA and approach of unsupervised cycle domain adaptation to learn from image to video. We all know that training the deep learning-based video models for action recognition requires a large amount of labeled videos, and the collection and annotation of large-scale video datasets is time-consuming and cost-intensive. In the meanwhile, there are a large amount of web images of human actions out there in the internet. They are really easy to collect by simply querying widely available commercial search engines. And unlike videos, web images usually capture the representative moments of events or actions and provide more diverse examples for the concept. So they are rich and highly diverse. Most importantly, the web images are labeling free. This makes them a good data source for video recognition. The problem of image-to-video adaptation uses webly labeled images as the source domain and the unlabeled videos as the target domain for action classification without a video annotation. However, there are two challenges in this setting. First, there is a spatial domain shift between web images and the video frames. This could be difference in image styles, camera perspectives, and semantic drifts. Second, there is modality gap between spatial images and the spatial temporal videos. This means only spatial knowledge can be transferred from source to target domain. To tackle these two challenges, we propose a cycle domain adaptation. We train an image model and the video model in a cycle. In this manner, we alternatively perform domain alignment on the image model to address the domain shift, and we perform spatial temporal learning on the video model to close the modality gap. We will introduce our pipeline step by step. First, we're given with the source domain of labeled web images and the target domain of unlabeled videos. In the first stage, we train an image model with the web images and the extracted video frames. Here we use an adversarial domain discrimination loss to reduce the domain shift. As the video frames are unlabeled, this is class-agnostic domain alignment. In the second stage, with this image model, we compute the pseudo-labels on all frames of the target videos. Then we aggregate the frame-level pseudo-labels into video-level pseudo-labels. With the video pseudo-label, we can train a video model on target videos. In the third stage, we use the trained video model to update the video pseudo-labels. Then we propagate the video-level pseudo-labels into frame-level pseudo-labels. In this stage, we have both web images with ground truth labels and the video frames with pseudo-labels. We perform cross-domain contrastive learning on the image model for class-aware domain alignment to align the samples on the category level, and this would further improve the image model. The fourth stage is the same as the second one. We use the image model to update the pseudo-labels for target videos, and further retrain the video model on the target data. And this completes our cycle domain adaptation. Here we provide some t-SNE visualizations to give an intuition how the different learning stages have an impact on the feature distribution. Here we show the image features on the top row and the video features on the bottom row. In Figure A, we show that for a source-only model without adaptation, the web images, which are the blue points, gather in category clusters after supervised training. However, the target video frames are far less discriminative and highly misaligned because of the domain shift. In Figure B, after PsycDA stage 1 of a class-agnostic domain alignment, the global alignment of a source and target features gets slightly better, but there is no sign of alignment on the category level. In Figure C, after the PsycDA stage 3 of a class-aware domain alignment, with the category knowledge, the alignment shows a lot better category-level association between source and target data. By passing pseudo labels from the image model of stage 1 and stage 3 to train on target videos, we get the corresponding video models in the stage 2 and stage 4. We plot their video features in Figure D and E. We see that after the PsycDA, the video features have more pronounced category clusters with large interclass distances. This shows the effectiveness of our method. By addressing the domain shift and the modality gap, our PsycDA manages to compare favorably with related work. For the task of image-to-video adaptation, we outperform the state-of-the-arts. We have more extensive evaluations on image-to-video adaptation and mixed source-to-video adaptation in the paper. Thanks for your attention.
Okay. Is the author here?
Hi, I am here online.
Hello. So
Hello.
is there any questions from the audience for the authors? Okay, so I have a question for you. Wait.
Yes, please.
So you use the supervised target for the images from the web. How is that label collected?
So you know that so on the most commonly used search engines for web images, one just type the keywords and you get like I don't know, millions of such web images whose annotation are just for free, right? This weak annotation of web images of the keywords or of the text.
Okay,
like for
so
example, when you search for the keyword, let's say climbing, then you get a lot of web images with the content of climbing.
yeah, okay.
Yeah, I mean, this is
that.
Yeah, this is the point of this image to video adaptation, that you can take full advantage of this free annotation of web images from the internet as a large source.
Okay. Thank you for your answer. Is there any other question for the author?
You're welcome.
Okay. Okay, thank you for your paper and presentation.
Thank you.
Okay, we will go to the next paper.
Hello everyone, we are going to introduce our paper called Take 1 gram of neural features, Get Enhanced Group Robustness. Imagine crowdsourcing an image dataset of camels and cows. Due to selection biases, a majority of cows stand in front of grass environments, whereas camels are found in the desert. If a deep classifier like ResNet50 is trained by minimizing the standard empirical classification loss, it will misclassify the following images. These unusual images depict rare situations in which a cow is standing on sand and a camel on grass. Without any form of regularization in the training algorithm, the obtained network will absorb the dataset biases. This is especially problematic for the classifier's robustness if rare occurrences are encountered. What we want instead is a classifier that will not confuse a cow standing in the desert with a camel and vice versa. Overall, this example allows us to introduce basic vocabulary of the challenge tackled in this paper, the Group Robustness Challenge. In this challenge, we find systematically majority groups and minority groups. The sand and grass context are called the environment, and a group is the intersection between a class and an environment. Ideally, we want high worst group accuracy while maintaining high mean accuracy. To obtain such a robust classifier, here is our approach. We introduce GramClust, a two-stage method which first discovers in an unsupervised fashion pseudo-environment in the training dataset, and then train a from-scratch classifier with a regularized, robust optimization objective. The environment discovery relies on a k-means clustering algorithm using normalized feature gram matrices at different layer levels. The robust training consists simply in minimizing the empirical classification loss on the worst pseudogroup defined from the previously discovered pseudo-environment. We detail here the first stage of Gram-Clust. Previous works observe that ERM tend to fit model on data presenting easy-to-learn spurious correlation at the beginning of the learning process. Hence, we start our approach by fine-tuning an ImageNet pretend model during only a few iterations to capture such correlation. For our training image, we extract feature maps from various layers of this model. Then, from each layer, we compute its gram matrix, which encodes visual correlation via an inner product between each pair of feature maps. We normalize this representation, concatenate them, and apply random projection to reduce the dimension. Finally, the resulting vectors are used as features of a K-means algorithm to partition the training dataset into pseudo-environments. We evaluate our approach on 3 image classification datasets with spurious correlation, standardly used to evaluate group robustness: Waterbirds, Celeb A, and Coco and Places. We follow standard protocol used to measure performance and report the test worst group and average accuracy for Waterbirds and Celeb A, and the in-distribution and shifted accuracy for Coco and Places. Our comparative results first show that ERM perform poorly on minority groups, as there is a large gap of performance between the average accuracy and the worst group accuracy. Methods which make the assumption of group annotation for training images improve group robustness over ERM, in particular group DRO, which achieves the best results. However, this assumption is a major limitation since in real-world application, this group annotation might be a priori unknown and, if known, ambiguous to define and expensive to annotate. Gram-Clust achieve state-of-the-art performance compared to all methods that do not use group labels on the training set. For instance, on Celeb A, it outperforms the second-best method, GTT, by 24.3 points. But more importantly, Gram-Clust also alleviates the need to use group annotation on validation data to select hyperparameters, as it relies on pseudo-environment labels given by the K-means clustering. In this experiment, we validate that using gram matrices provide finer information about environments than relying on the mean and variance of each feature map, sometimes used in neural site transfer as an alternative method, or using the penultimate representation of a ResNet 15 identification model. As a conclusion, we observe that gram matrices are indeed effective to capture environment information, and our proposed method, Gram-Clust, is easy to scale and also alleviates the need of ground truth labels even on a small validation set. And our experiments show that it outperforms all recent baseline to address group robustness without annotation. And thank you for your attention.
Okay. Is the authors here?
Yep, we're here.
Yeah, okay, I see. Is there any questions from the audience for the authors? No, actually, I have a question for this paper. So you are using K-means on the feature on the gram matrix of the features as a grouping. Have you ever tried other clustering algorithm such as dbScan instead of K-means?
Yep, we try all the clustering algorithm. In fact, we also try in our supplementary the spectral clustering also, and we actually found similar results. So we went for the K-means as it was also the most scalable for our task.
Okay, thanks for the answer. Is there any other questions from the audience? No, okay. Then we will go to the next paper. Thank you for your presentation.
Hi everyone, I'm Yifan from Chinese Academy of Science. Today I will present our study domain-specific risk minimization. We focus on out-of-distribution generalization problem where the training distribution and test distribution are different. Recently, many works seek to learn environment representations for better generalization performance. The starting intuition is here. The risk under the target domain is bounded by a weighted empirical risk on source domains and source domain divergence and lambda alpha. This term is dependent on the choice alpha of hypothesis space. So previous works believe that if the empirical risk on the source domains and source domain divergence can be minimized, then the risk on the target domain can also be bounded. However, this bound depends on the hypothesis space, as I said before, and the bound cannot take care of the labeling function shift. Here we provide a simple counterexample. Here we have two source domains, red and blue, and two target domains, orange and green. The classification boundary is drawn by the pink color. Namely, if x1 is smaller than -3 or x1 is larger than 3, it belongs to class 1, otherwise class 2. So if we learn an invariant representation among the red and blue, then the invariant representation will be learned in figure B. However, the labeling function of these two source domains are different. So whatever you learn a classifier here, it will lead to a large joint error on these two source domains, let alone the target domain. It is a simple counterexample. To this end, we will first construct a new generalization upper bound for the target risk. Our upper bound have two terms, and the first term is weighted source error, and the weight is the density ratio between the target domain and the source domain. The second term measures the difference of the labeling function directly. Our new bound does not depend on the optimal hypothesis space, and it can directly reflect the influence of labeling function difference. The new upper bounds motivates our methods, the domain-specific risk minimization. Here is the training and test pipelines. Here we introduce the training pipelines first. Motivated by the first weighted risk minimization term, we can use specific classifiers for each domain, and then it has more freedom and the source errors can be further reduced. Besides, if we use specific classifiers, we can see in figure C. Here, we can learn two joint classification boundary, and the classification problem can be perfectly solved. Besides, we also want to minimize the second term to minimize the labeling function difference. During test, we have multiple classifiers can be used. So in this stage, we can use the minimal entropy selection strategy. This strategy selects a proper classifier for the test image with a minimal prediction entropy. In this way, we can approximately to minimize the labeling function difference of two domains. We evaluate our framework on the columnist dataset, and the performance is superior to ERM and ARM. Besides, the source domain accuracy rate is very high. Thanks for your attention. Any questions?
Okay. Thanks for the presentation. Is the authors here?
Yeah, I'm here.
Yeah.
Any
Okay.
question?
Yeah. Any questions from the audience?
Yeah. Hi, Ethan. I have a question.
Yeah.
Yeah. So you use the model selection in your method, and I'm wondering if when the target domain is far from the source domain, will this model selection still work well?
That's a good question, but I think recent works cannot work well also under the setting when the target domain is far from the source domain. So our framework, it works well on when your source domain is not so far from target, you know. Because we don't have any representation term, and we just to select a proper classifier to the target sample.
Okay. Yeah, thanks for your answer.
Yeah, thank you.
Okay, thanks for the question. Is there any more questions from the audience? No. Okay. Thank you, Yifan, for your paper.
Yeah, thank you.
We will go to the next poster.
Hi everyone, I'm Yifan. Here I will present our work, Generalizable Person-Read Fiction without Demographics. Person-read fiction belongs to a subproblem of image retrieval. But distinct from image retrieval, the goal of person-read fiction is to retrieve a specific person in the gallery set. Recent person-read fiction tasks can be divided into 4 categories: supervised learning, single source documentation, domain generalization, and proposed domain generalization without demographics. Our setting also contains multi-domains, but the domain partition is unknown. We first introduce some basic knowledge about distributionally robust optimization. DRO is a kind of efficient tool for learning generalizable models. Its purpose is to optimize the worst-case performance among a distribution set, namely the uncertain set Q here. Q is often defined as a collection of distributions that is near to the training distribution. If we set a very large radius, then the Q will contain many distributions, and the distribution has a larger probability to contain a test set, and then the generalization performance will be better. However, if the radius is small, then the Q will reduce to the training distribution, and the object of the DRO will reduce to the empirical risk minimization. However, DRO also has some problems. If the radius is large, then the distribution set includes many unrealistic or useless cases, which will make the learned model refuse to make a decision. In contrast, if the radius is very small, as I said before, the DRO objective will reduce to empirical risk minimization and will not benefit the generalization capability. Here we conduct simple experiments with KL-DRO. KL-DRO is a KL convergence constraint DRO. Its uncertain set P is constrained by a KL divergence constraint. Namely, its uncertain set is a KL ball then centered at a training set with radius eta. However, directly use the KL-DRO object as our object function, the performance will not better, and even worse than the baseline empirical risk minimization. The reason behind this phenomenon may be that the object of KL-DRO is based on some unrealistic assumption, such as strong convex, which cannot work on our parametric neural network. To this end, we propose to reformulate the KL-DRO objective. Here we apply a simple change of memory trick to get the tendency ratio, and on the mode assumption we solve the inner optimization, namely the maximization process, and get the closed form solution. The following objective function will be a weighted empirical risk minimization, and the tau star and the eta should satisfy the following constraint. However, here we still have 2 problems. The first one is that taking the expectation over the whole training dataset is untractable, and the tau star is hard to estimate or to calculate. So we propose 2 approximations. Firstly, we sim the tau star as a hyperparameter and decrease the value as our training process. The second one is we maintain a queen, here the M. We maintain a queen to store the history weights and avoid to calculate the expectation over the training set. It's rather a better estimator of the normalizer than estimated by one batch. With this simple reweighting method, we can obtain superior generalization performance on several person-read fiction benchmarks. Besides, our method doesn't doesn't depend on demographics such as domain index, camera index, and so on. Here are our test and evaluation results, and UNITRO is shown to be able to learning more invariant permutations compared to competitive baselines. And that's all. Thanks for attention.
Okay. Hello again, Ifan. That's also your paper.
Yeah.
Is there any questions from the audience? Okay. I have one question. So
okay,
it seems that the unit DRO is a modification of the KL DRO model.
Yeah, exactly.
Can this method be applied to like a different models other than KL DRO?
What is in the different models?
Like other models for this problem, for this generalizable person ready.
Oh yeah, exactly. It can generalize to other benchmarks. Actually, we test the proposed. It is indeed a reweighting methods, and it can be incorporated to any other dimensionalization methods. And we also conduct experiments in our paper on domain-bound benchmarks such as color laminates and so on. It works well.
Okay, thanks for the answer. Okay, we will go to the next paper.
Hi everyone, welcome to our presentation. I'm John Zhang from KAIST, and today I will introduce a simple idea we found useful to improve many types of robustness of neural networks without relying on specific priors on it. So here are our key motivation. The motivation is how to better abstract the threat model of more natural corruptions beyond the adversarial examples. In a sense that how the threat model of adversarial examples are defined. So here we can see that usually the adversarial threat model is defined by a constraint on a norm-bounded model. So and about to maximize some cross entropy, for example, to generate some to define a channel that noisy channels on it. One of the possible ways to generalize this notion for wider corruptions is to consider a constraint on mutual information of X with respect to Y, instead of just considering the norm-bounded notions, so that any corruptions of X do not actually affect to the final correlation with Y. At the same time, we can minimize the mutual information of Y with respect to the fx, the embedding, so that even if the x contains enough information with respect to y, but after we forward it to the fx, there's no information remaining to y. Once we have this, we can naturally consider an adversarial training with respect to this threat model, but the challenge here is the computation of feasibility, of course. But here we can still see that what we essentially need is to make sure that the y correlative signal in x could be preserved until z as much as possible. So that is a key motivation of why we consider a nuisance representation, here we call it Zn, as well as the original embedding of z. Our approach is basically threefold. First, we make sure that combining z and zn can recover the full information of x by maximizing the mutual information. And next, we force zn not to encode any y-related signal, instead let z can do it. And finally, we compress the z as much as possible so that the solution could not be degenerate by minimizing all the information of zn to z. We also propose a practical autoencoder-based architecture to better implement the objective, which is applicable for both convolutional and transformer-based models, as well as a practical training loss, which is an basically extension of variational information bottleneck objective. We did evaluate our method. We called it as NIPAE in various aspects of model robustness, as here we highlight for some of them specifically for corruption robustness and out-of-distribution detection. And you can find more results in the paper, for example, for an application for certified robustness by combining our representation with randomized smoothing technique. For the evaluation of corruption robustness, we observe our objective, which is built upon variation information bottleneck, or VIB, could consistently improve over VIV in terms of the corruption errors. And the results are remarkable in the sense that the gain can be even better than a recent method of augmix, which leverages somewhat additional prior augmentation pools in training. And from our observation that we could actually further improve our results by combining those methods like augmix or more recently pixmix, this shows that our improvement can be seen as an independent of those. We also show that our method could better generalize on other types of distribution shifted CIFAR10 datasets compared to pixmix, for example, as well as its ability to scale up to larger scale dataset, as shown in the results from ImageNet-C or R and S. In terms of out-of-distribution detection, we show that our the nuisance embedding can actually define a really strong score or out-of-distribution score based on its likelihood, and show that is a significantly improved results from a recently proposed challenge benchmark of object, which considers CIFAR10 as a test set, as well as the CIFAR10 corruption or ImageNet-10 as an additional in-distribution data set. So it is important to distinguish between hard in-distribution data set and out-of-distribution. And this is a summary of this presentation. We welcome any questions and comments through this context, and thank you for listening.
Okay, that's a presentation from the author. Is the author in the Zoom? I don't see them. It seems the author is not here. So we will go to the next poster.
Hello everyone, my name is Oliver Hahn and I'm going to present our paper, Semantic Self-Adaptation, Enhancing Generalization with a Single Sample. This is a joint work with Shervin Bahmani, Edward Samfir, Nikita Raslanov, Daniel Kremers and Stefan Roth. In this work, we consider semantic segmentation, the task of predicting a distinct semantic class for every pixel in an image. This dense prediction task is particularly challenging in the setting of out-of-domain generalization. Hereby, the training is typically performed on an inexpensive synthetic data, whereas real-world data is observed at inference time. Previous studies rely on the assumption of a non-adaptive model, meaning once the training process is complete, model parameters remain fixed at test time. We challenge this premise, inspired by the idea of adaptive grasping, where a robotic gripper uses an observation input to adapt its technique to the object being grasped. Similarly, our self-adaptive approach for semantic segmentation adjusts the inference process to each input sample of the test data, without sharing any knowledge across the test samples. We chose WildDash as our validation set, which bears closer visual resemblance to the target domains, while still having a distinct distribution from the test domains. We train a model on the synthetic datasets GTA and Cynthia, and evaluate on 4 different test domains, namely Cityscapes, BDD, IDD, and Mapillary. Based on the original test image, we create a mini-batch of augmented samples by using multiple scales, horizontal flipping, and grayscaling. We pass this augmented mini-batch through a model pre-trained only on synthetic data. Using inverse similarity transforms, we project the obtained semantic maps back to the original image plane. This leads to having multiple predictions for each pixel. Next, we compute the mean of the softmax probabilities along the batch dimension, and introduce a class-dependent threshold. This allows us to extract the dominant class for each respective pixel, ignoring low-confidence predictions. The generated pseudo-label is used to fine-tune the model for a fixed number of iterations. After this self-adaptation process, we compute a final prediction for the test sample using the updated model. To remain within the domain generalization paradigm, we discard the model changes after every test sample. When analyzing batch normalization layers, running statistics from the synthetic source data differ substantially from test domain statistics. To mitigate the covariate shift problem, we introduce self-adaptive normalization, which improves the test time behavior of batch normalization layers. We compute a weighted sum of mean and variance accumulated during training from the source domain and statistics extracted from the single test sample. Our self-adaptive normalization, or SAN for short, does not only lead to better out-of-domain accuracy in terms of mean IOU, but also to better model calibration, measured by the expected calibration error, abbreviated as ECE, reported in this table. Despite having a stricter evaluation practice and a simpler model architecture than most published work, self-adaptation overwhelmingly exceeds the segmentation accuracy of very recent work. On average, self-adaptation surpasses its ResNet 50 baseline by 12.7% IAU and improves the previous best method by 1.03% IAU on average. Modifying the inference process inherently changes its runtime. We profile the runtime of the baseline model and our proposed self-adaptation. We further compare our approach to the test time augmentation, short TTA, as well as model ensembles. For a fair comparison, TTA and model ensembles use our proposed self-adaptive normalization scheme. Furthermore, we also investigate ensembles in combination with TTA. We observe an expected increase in runtime using our self-adaptation due to the additional model updates, but self-adaptation naturally offers a trade-off between increased runtime and achievable accuracy. Nevertheless, our self-adaptation proves to be not only more efficient than the model ensembles, but even more accurate. In the following, we visualize the performance gain of self-adaptation on a video sequence taken from the Cityscapes dataset. We observe a clearly perceivable improvement over the baseline, especially in terms of image boundary consistency. Our approach exhibits more homogeneous semantic masks with visibly fewer artifacts than the baseline. To summarize, we find that self-adaptation improves out-of-domain generalization accuracy of state-of-the-art methods. We further obtain an efficient accuracy and uncertainty boost by using our self-adaptive normalization. We show a robust and strong accuracy improvement agnostic to training pipeline and model architecture. While we still suffer from increased runtime, we offer a cost-effective runtime accuracy trade-off. We hope that these encouraging results will motivate our research community to study self-adaptive techniques in other application domains and increase the efficiency towards real-time. The code and pre-trained models are publicly available, and we hope you find them useful in your work. Thank you for watching.
Okay. Is a paper here? Is a paper authors here?
Yes.
Yeah, okay. So I see there's the question in the chat. Is this? So the question in the chat is, how would you recommend to do such sorry. So I'm working on my own autonomous vehicle and have my own data. And obviously it have no OOD data set. And how would you recommend to do such a process in real world data? Especially how would I evaluate it? Can you see the question in the chat?
It seems like it's just a general question to, I guess, everyone, since we're all working out of distribution generalization.
Yeah, so, okay. So it's not a question about your work, sorry.
But I guess maybe I cannot still answer this question. I think,
yeah, okay.
So in my opinion, domain generalization approaches, especially if we're thinking about deploying them in real time, they're still quite limited. However, domain adaptation approaches where you can pre-record data of the environment in which you'll potentially deploy your system, and then training the model offline in an unsupervised way, but has pre-trained it on synthetic data, would probably be more effective ultimately. But that, of course, requires you the knowledge of where the system will be deployed, and so in the ability to record data in that environment.
Yeah, that's a very good answer. Thanks for answering this question. So we are running on a tight schedule, so we have to go to the next paper. Thank you for presenting. Okay.
Hello, I'm Andre. I'm excited to tell you more about our new method for source adaptation. This is joint work with Vita and team and was part of my internship at Samsung AI in Cambridge. We focus on the source-free annotation setting that has recently attracted a lot of attention and consists of adapting a model pre-trained on the source dataset to unlabeled examples from the target dataset. Source-free adaptation is typically slow and uses backpropagation, which makes it challenging to perform source-free adaptation on edge devices such as smartphones. Our solution addresses this challenge by computing prototype of class and domain shift and using them for classification of target domain data. The approach is simple, fast, and purely feed-forward. It leads to strong improvements in accuracy at small fraction of time with existing methods and is a new baseline for source adaptation and at the same time a practical strategy for edge devices. We name our method prototypical domain adaptation or PDA. As part of the method, we construct the prototypes by using a pre-trained model to extract the features and pseudo-labels. We only use examples predicted to be of a given class to calculate the class prototype, and the examples with larger confidence contribute more. Predictions are made by extracting features from the test example and finding the closest prototype using cosine distance. We also consider an extension that uses robust adjective classifier based on minimum covariance determinant to obtain higher quality pseudo-labels. In this case, ROG replaces the pre-trained classifier and is only used for creating the prototypes. Parameters of ROG are estimated using the features and pseudo-labels given by the pre-trained model when applied on target domain data. We evaluate our approach on three common benchmarks: Office, Office-Home, and VisDA-C. We consider a number of baselines. First, directly using the pre-trained model. Second, updating the benchmark statistics using the target dataset. Actually, in our method, we update the benchmark statistics as well, so it's also part of PDA. And finally, shot-based backpropagation-based methods, which are only given for context, as they are not really our direct competitors. We can see that BN update leads to a relatively small improvement compared to directly deploying the pre-trained model. However, both PDA and PDA MCD lead to large improvement over the pre-trained model and achieve target domain accuracy relatively close to the backpropagation-based methods at a small fraction of time, as we will analyze soon. The results on Office-Home are similar, although in this case the backpropagation-based methods have a larger margin. PDA and PDA MCD also lead to large improvements on large-scale VisDA-C cinetic to real benchmark. Now it's time to analyze this method a bit more, and we start by analyzing the time needed for adaptation for all the approaches that we consider. We can see that the time needed by PDA and its extension is negligible compared to the backpropagation-based methods and is very similar to simply updating BN statistics. We also investigate the upper bound on performance of PDA that we obtain when using true labels rather than pseudo-labels. We can see that there is a lot of further space for improvements and to potentially even outperform expensive backpropagation-based methods. Finally, we analyzed if we could directly use ROG classifier based on MCD instead of prototypes. The answer is that this approach has some benefit, but it's not as strong as our PDA method. To conclude, we have presented a new simple method for feed-forward source annotation that is based on computing prototypes of different classes under a domain shift. It leads to strong results and takes only a small fraction of time to run compared to standard backpropagation-based methods. Finally, evaluation with true labels has shown that there is scope for developing further new feed-forward source-free annotation methods, for which our method acts as a well-performing baseline. Thank you very much.
Okay, so that's the presentation. Is the authors here in Zoom? Okay, seems like the authors are not here. Then we will go to the next paper.
Hello everyone, today I will be presenting our work on intrinsic multimodality for domain generalization. This work is in collaboration with Shivam, Milan, Balaji and Dr. Vineet. We address the problem of domain generalization, which refers to the task of learning a model using data from source domains in order to generalize and predict effectively on an unseen domain. Most prior and current state-of-the-art approaches address the DG by using different learning paradigms and training strategies to learn domain-agnostic semantic features that represent an object category and thus can be extended to unseen domain samples at test time. Following figure illustrates the DG setting, where in training time you have a set of examples belonging to different source domains. For example, here sketch, cartoon and painting, and a test set belonging to an unseen domain. For example, photographs here. Recent progress towards the weakly supervised vision language models like CLIP have shown that their abilities on semantic understanding and have also triggered the interest in using them from practical uses in various settings. These methods are known to learn holistic object representations from cheap, weakly supervised noisy text annotations that capture class-level semantics of the object categories such as shape and content. Such representations can thus inherently capture object characteristics that generalize to unseen domains. We leverage this potential of vision language models in this work, and motivated from this, we study how multimodal information in pre-trained multimodal networks can be leveraged in an intrinsic way to make systems robust to domain shifts as well as enhance their generalization to unseen domains. To be specific, we propose intrinsic multimodality for domain generalization, a simple and elegant way of leveraging the intrinsic modality present in these pre-trained multimodal networks along with visual modality in order to generalize to better unseen domains. We perform comprehensive experimentation on standard DG benchmarks like DomainNet and Office Home and show that Indigo achieves new state-of-the-art by outperforming prior state-of-the-arts conventional techniques like transfer learning, fine-tuning, and zero-shot. Following figure provides a broader illustration of our idea. In DG settings, since we don't have access to explicit modalities like image captions for the source domain data, we leverage the intrinsic modality present in the pre-trained multimodal networks along with the visual modality obtained from the image. Our approach involves three components. The first one is the multimodal branch, where we leverage a pre-trained large-scale vision network like CLIP that uses a contrastive learning objective to push embeddings of matched text pairs together and non-matched pairs apart. Since in DG we don't have direct access to text annotations, we can assume that an image unnormalized projected embedding of CLIP vision encoder would be weakly aligned with the image's hypothetical text description. This allows us to leverage the intrinsic modality present in the pre-trained multimodal vision transformer in form of its unnormalized projected embedding. The second component is the visual branch, which is a sibling of the multimodal branch. We employ a trainable vision transformer to learn a visual concepts from source domain that might be absent in CLIP representations but are relevant to the task. These concepts can be data, domain, or even class specific, which when combined with the intrinsic modality obtained in the previous step can help boost the overall performance on the given task. Further, since VITs are better than CNNs in recognizing shapes, their shape bias representations will further assist our overall pipeline in generalizing to unseen domains. The last component of our pipeline is the fusion module. The purpose of the fusion module is to fuse the intrinsic modality and the visual modality and perform the final classification. To achieve this, it uses a multi-head self-attention blocks and feed-forward networks to perform intermodality attention. This attention mechanism thus allows the intrinsic modality to attend with the visual modality and incorporate any dataset, domain, or class-specific concepts present in it. Similarly, the visual modality will interact with the intrinsic modality to learn multimodal concepts present in it. This ensures that the final representations leverage the best of both modalities. Here we show our results on DomainNet and Office Home datasets. We perform experiments on these two datasets and compare against recent state-of-the-art techniques in DG as well as conventional approaches like transfer learning, zero-shot, CLIP. As we can see through the table, Indigo achieves new state-of-the-art results by outperforming all the compared methods by good margins. In particular on challenging domains like Quick Draw, where the conventional ways of using CLIP perform worse than prior arts, Indigo achieves the best performance by leveraging the best of both modalities. In order to highlight that the Indigo is leveraging the visual modality, we perform an ablation where we vary the strength of the VIT used in a visual branch. Additionally, we also vary the number of layers used in the fusion module to show its effect on the final performance. As shown in the table 2, by using more powerful and large vision transformers in the visual branch, the domain generalization performance of Indigo improves. This shows that the Indigo can also attend to visual modality to learn additional shape-biased concepts, and performance is not solely because of the intrinsic modality. Further, we can see that the gain in the performance becomes more prominent when the more layers are used in the fusion module, implying a better intermodality interaction between intrinsic and the visual modality. At last, we analyze and compare the representations learned by Indigo with DIT and CLIP on target domain for 25 classes of Office Home via TSNE plots in figure 3. As we can see, for Indigo, the plot is less noisy and well segregated into class clusters as compared to the DIT and CLIP features, resulting in the state-of-the-art generalization on these target domains. Thank you for listening to the end, and please scan the QR code for reading the whole paper.
Okay, that's the presentation from the author. Is the author in the Zoom?
Yeah.
Okay. So the author here, is there any questions for the authors?
Yeah. Hi, Punan. I have a question. Thanks for your
Yes.
nice work. And I saw in your model the image is also the input of the multimodal branch, right?
Yes, you are right.
So can we understand that it's also something like the improve of the performance can also come from the larger capacity of the network, or it's something like we ensemble two model. One is the VIT model and the other is the MM branch model.
Right. So yeah, you are right on the path. Like the majority of the improvement is definitely coming from the multi-model branch, and the main motivation of using was that these models have recently shown to be better at these domain generalization tasks. What we did was kind of extend it, because let's say in case you want to use such kind of pre-trained models, so the very conventional ways of using such models will be something like transfer learning, zero shot, or fine tuning. But if we can somehow use a better strategy to maybe couple additional vision transformer, which is approximately using the same number of parameters, and somehow fuse these two representations into one, that's what we kind of focus on. We show that these performs better at domain generalization tasks than standard zero shot, fine tuning, or even transfer learning, just a base pre-trained multimodal network. So yeah, and like in ablations, we have definitely shown that how if you kind of change the architecture of these vision transformers, right, you keep this multimodal branch fixed but change the visual module, the performance gets affected. So if you use a more stronger, let's say hybrid VITs instead of just normal VITs, you tend to get better performance. So yeah, that definitely kind of highlights the fact that there's something that is being leveraged from the VITs, and definitely the fusion module is also happening, because the more layers you have, the better they are being interacting with the both intrinsic as well as the visual modality.
Okay, thank you for the answer.
Yeah, no problem.
Okay, we will go to the next paper.
Hi, my name is Ashwin, and I'll be presenting our paper with my colleague Rahul, which is titled The Value of Outer Distribution Data. Does more data always help? We tend to procure more data to improve generalization on a desired task. However, real datasets are often heterogeneous due to flawed annotations or due to geometric and semantic nuisances. This could lead to the presence of out-of-distribution samples in a curated dataset, which can worsen generalization error on the target task. How do we model the heterogeneity in data? We assume that our dataset D comprises of n samples from the target task and m samples from an out-of-distribution task. We seek a hypothesis H that minimizes generalization error on the target task, which we denote here as ET. We do not know which samples are from the target task, and which are from the OOD task. Hence, we select a hypothesis trained to minimize the empirical risk on all the samples from D, which includes both target and OOD samples. Let's consider a simple problem where we consider the OOD and target tasks to be Gaussian mixture models. The tasks are binary classification tasks with one-dimensional inputs. One class is from the red Gaussian and the other class is from the green Gaussian. Our goal here is to build a linear classifier that separates the two classes. We consider a family of OOD task distributions, which are horizontal translations of the target task distribution by a delta amount. We then ask the question, for different values of delta, what trends do we see in the generalization error on the target task when we train on both target and OOD samples? Then we ask the question, what impact does OOD data have on the generalization error on the target task? For the described target and OOD task distributions, we can compute an analytical closed-form expression for the generalization error on the target task thanks to the simple nature of our problem. The x-axis in the plot varies the ratio of OOD samples for a fixed number of target samples, and the y-axis is the generalization error on the target task. Each curve corresponds to a different OOD task with a different translation delta. For larger translations, like the yellow curve, the OOD task is far away from the target task, and hence most OOD samples are detrimental to the generalization error. As expected, a nearby OOD task can improve generalization error. However, interestingly, for many of these tasks, the generalization error on the target task is a non-monotonic function of the number of OOD samples. In other words, some samples help, but too many of them would hurt the generalization error on the target task.
Why does non-monotonicity occur? Intuitively, it is the result of a bias variance trade-off. If we add more OOD samples, we reduce the variance. However, this also increases the bias since the difference between the two distributions becomes more apparent. We visualize this trade-off in the plot on the right. Non-monotonicity is also observed in real datasets and occurs due to geometric and semantic nuisances. For example, we show that they occur in benchmark domain generalization datasets and on datasets constructed from CIFAR-10. How do we handle non-monotonic trends in data? Assuming we can separate the data into target and OOD samples, we consider the following weighted objective. We use alpha to weigh the target empirical risk and 1 minus alpha to weigh the OOD empirical risk. We can derive an approximation for the optimal value of alpha using an upper bound for the generalization error. In the expression, rho is the ratio between the difference between the two distributions and the measure of model capacity. If the target and OOD tasks are very different, or if the model capacity is small, we should set alpha to 1, and that effectively discards all OOD samples. Otherwise, we appropriately weight the OOD samples and the target samples. However, in practice, we treat alpha as a hyperparameter and find it using grid search. On each of the datasets, we plot a generalization error against the ratio of the target and OOD samples. The red curve corresponds to treating all samples as though they are from the same distribution, that is alpha equal to n by n plus m. The yellow curve corresponds to alpha equal to 0.5 and the green curve to the optimal alpha. Across the 4 different datasets, the green curve, which considers optimal alpha, has a monotonic decreasing trend in the error. And as we continue to add more and more OOD samples, the generalization error on the target task reduces. In conclusion, the generalization error on the target task can exhibit non-monotonic behavior. Additionally, using a weighted objective allows us to circumvent this non-monotonicity and exploits the additional OOD data. For more details, check out the linked archive article.
Okay. Is the authors here?
Yes, I'm here.
Yeah, okay. Is there any questions for the authors?
Hi, I have one question. Thanks for authors for this very interesting finding. And in the experiment, I saw that the authors used some like handcraft OOD data, for example, manually turn the image by a certain angle. I'm wondering if we are in the real world and how we can verify this finding in the real world data? For example, there are some real world out of distribution data. How can we also see this trend of result?
Sure. So to prove our as a proof of concept, we use, like you mentioned, we use the rotated images as the OOD data, and we also use blurred versions of CIFAR10 as OOD. And apart from that, to sort of mimic the real world data, we also used the domain generalization benchmark domain bed and the data sets tax and domain net to evaluate this construct. And then we found that for some certain combinations of target and OOD pairs, we noticed this non-monotonicity occurring as well. And apart from that, we also have an experiment which we did not include in the slides, which includes a dataset called Scenic, which comprises of two sources of data, one from CIFAR10 and another one from ImageNet. And then we also noticed, even though we did not see a non-monotonicity yet, we noticed that when we train on a combination of CIFAR and ImageNet images, and then test on CIFAR test set, we noticed that the generalization error hurts a bit when we use more and more ImageNet samples in our training mix. And recent works such as metadata archaeology and deconstructing distributions. So unfortunately, we don't cite them in our presentation, but they have recently found out that methods of like profiling each data point of the data set into 4 baskets, non-compatible and noisy, and I can't remember the exact categories, but one future work that we hope to pursue is to categorize points based on these profiles and see whether this non-monotonicity could occur inside data sets. So yeah, that's something looking forward. Yeah.
Cool. Thanks for your nice work.
Thank you.
Okay, thanks for the presentation and the questions. We'll go to the next paper.
I'm Harsh. In this talk, we present a closer look at smoothness in domain adversarial training. This is joint work with Sumuk, Mayank, Aryan, and Professor Babu. For deep neural networks, a model trained on labeled images from a particular domain, example webcam, performs poorly on images from another domain, examples coming from Amazon. Domain adaptation refers to algorithms of model adaptation
Sorry, the sound is problematic.
adversarial training refers to performing domain adaptation by learning representations which are invariant to source and target data, such that the classifier is also able to work well on target data. The network is composed of a feature extractor, classifier, and a domain discriminator. The task loss on classifier is usually a cross-entropy loss. The adversarial loss on discriminator is binary loss,
Okay, it seems that this video, the audio is.
The network is trained to minimize a combination of task loss and an adversarial loss. It has been shown that flat minima lead to better generalization compared to sharp minima for supervised learning. In this work, we analyze the effect of smoothness, that is, flatness enhancement, for domain adversarial training. The task loss can be seen as expected cross-entropy loss or MSE loss. We first analyze the effect of enhancing the smoothness of task loss with respect to network parameters. We compute the properties of Hessian of the task loss to analyze the loss landscape. We plot the eigenspectral density of the Hessian to analyze the landscape. The plot of eigenspectral density for DAT with Adam and DAT with SGD and a smoother version of DAT. Low lambda max and low trace of H as we move towards right indicates convergence to smooth region, which results in improved accuracy on target domain. We find that lambda max increases is the domain adversarial training becomes unstable and leads to a drop in validation accuracy, as shown on the right. We observe that smooth not only improves performance on the target domain, it also leads to much stable training, as shown by low lambda max and stable validation accuracy curve, as shown in red on the right. Now let's analyze the effect on smoothness enhancement for the adversarial loss. The adversarial loss is a binary loss which differentiates between source and target. We show theoretically that smoothness enhancement leads to a suboptimal discriminator. Further, empirically, we also find that smoothness enhancement, that is increasing rho on the right, leads to reduction in generalization performance on target domain. We now first introduce sharpness-aware minimization formulation, which can be used to modify any objective LOBJ in such a way that the solution converges to a smooth minima. We then use it to introduce the proposed smooth domain adversarial training objective. This SDAT objective focuses on only enhancing smoothness for the task loss, leaving the adversarial loss unchanged. SDAT can be easily integrated with a few lines of code change as shown on the right. SDAT also leads to significant improvement across variety of domain adversarial methods, as we'll see later. We now show results on full Office Home dataset. Our proposed smooth version of algorithm, that is CDAN with SDAT and CDAN plus MCC with SDAT, results in improved performance over baselines by a significant margin. We observe that with VIT backbone, the SDAT variants outperform baseline by as high as 3%. As Office Home is a relatively small dataset, to test the effectiveness of our method, we test our methods on the domain-net dataset. Here too, SDAT is able to improve over baseline significantly. In comparison to recent methods of TVT and CUTRAS, SDAT can achieve SOTA performance when combined with CDAN plus MCC, a simple DAT method. Due to its simplicity, it requires less GPU memory and additional modules, which makes it an effective practical choice for users. We introduced smooth domain adversarial training SDAT, which is effective, easily integratable, and a practical way of improving performance of domain adversarial training-based methods.
Okay, sorry. This video file seems has a very low volume. I already set my volume to high, but it's still too low. But if the authors is here.
Yes. Can you hear me?
Yeah. Yeah. Thanks. Thanks for being here. Is there questions for the authors?
Yeah, I have a simple one. So the authors proposed the method to use a smoother loss curve, right?
Yes.
So you think that this can benefit optimization procedure or like other aspects? How do you think this will make the domain generalization better?
Yes. So we think that like the domain discrepancy measure that we do with this smooth optimization measures, the smooth hypothesis space, that is very efficient and much better when we use this smooth optimization algorithm. So this allows us to have stable adversarial training for domain adaptation and domain generalization.
Okay. What if I just control the gradient when I train the model? So will that achieve a similar result?
You control the gradient?
For example, when it's too big, I cut it.
Okay. So yeah, so those basic methods are unable to like perform give effective gains. This sharpness aware minimization, SAM-based methods, they are much more effective in like doing the finding the flat or the smooth regions in the optimization landscape, and they get good effective gains. So even like in this current ICLR, we have few papers which use this method to get better gains over the normal domain adversarial training methods.
Thank you.
Okay, thank you for the presentation. Sorry, the audio went wrong. Okay, that's all the papers we have accepted for the poster session, and we will take a lunch break and come back at 1:30 p.m. for the calendar winner announcement. Thank you.